Hello everyone. It's a dreary day up in Edinburgh. The sky is overcast, it's drizzling constantly. In other words, it's a great day to do some programming. So let's do some more Advent of Code. For those of you who haven't been following along, we're solving Advent of Code. This is a programming competition of sorts. It runs between 1st and 25th of December. Each day we get a new problem, and each problem has two parts, although we can only see part 2 after solving part 1. We've been solving these tasks every day on the day. And we're solving them in Elixir Livebook. This is a really nice little web app. You can write a bit of code, and then Livebook will execute it and show you the result underneath. This makes writing code and exploring very easy. And then it has some... it's a bit like writing in an interpreter on the command line, except you can edit your code much easier. And honestly, I think it looks pretty nice on stream too. Now, Livebook can also do some fancier things, like say here we're generating a text area input, then we can write something into our text area, and then later we can just read it. And I think this is much nicer than hard coding strings like this into your source code or shoving them into random files and then having to read them. So going back to Advent of Code, we're trying to save Christmas by fixing the snow machine. However, in the 7 days up to today, we've done everything other than fix the snow machine. We've gotten launched out of a trebuchet, played a game with some cubes, with some colored cubes, fixed the gondola machine to go up a mountain, but then instead found ourselves going up to a sky island, helped an elf calculate his scratch card winnings, we helped another elf avert a famine on a different island. Then we played a ship racing game where the ships could only go a few millimeters forward every race. And yesterday we played poker. We played the kind of poker where 5 of a kind is a valid hand. It's been quite a ride, but I don't think we're going to be fixing Christmas, unfortunately, because we're doing everything other than that. Anyway, let's see what today is all about. Day 8, Haunted Wasteland. You're still riding a camel across a desert island when you spot a sandstorm quickly approaching. When you turn to warn the elf, she disappears before your eyes. To be fair, she had just finished warning you about ghosts a few minutes ago. We were riding on a camel with an elf and playing poker. One of the camel's pouches is labeled maps. Sure enough, it's full of documents, your puzzle input, about how to navigate the desert. At least you're pretty sure that's what they are. One of the documents contains a list of left-right instructions, and the rest of the documents seem to describe some kind of network of label nodes. It seems like you're meant to use the left-right instructions to navigate the network. Perhaps if you have the camel follow the same instructions, you can escape the haunted wasteland. Oh, so are we actually going to do a graph problem for once? Maybe but the graph problem doesn't sound like it has left and right. Well, let's see. After examining the maps for a bit, 2 nodes stick out, AAA and ZZZ. You feel like AAA is where you are now, and you have to follow the left-right instructions until you reach ZZZ. This format defines each node of the network individually. For example, RL, we don't know what RL is, and then AAA equals tuple of BBB CCC, so presumably left and right. Then BBB goes to D, DD, and EE, and so on. Oh, and ZZZ loops back on itself, both left and right, as does GGG, as does EEE, as does DDD. Okay, I have no idea what this is. Let's read on. Starting with AAA, you need to look up the next element based on the left-right instruction in your input. In this example, start with AAA and go right by choosing the right element of AAA, CCC. Then L means choose the left element of CCC, ZZZ. By following the left-right instructions, you reach the ZZZ in 2 steps. Of course, you might not find the triple Z right away. If you run out of left-right instructions, repeat the whole sequence of instructions as necessary. RL really means RL, 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 and so on. For example, here's a situation that takes 6 steps to reach triple Z. LLR, LLR, so we start with triple A, then we go left. Then we go left again and we find ourselves back in AA. Then we go right and we are now in BBB. Then we go left and find ourselves in AAA. Then we go left again and find ourselves in BBB. Then we go right and we end up in ZZZ. Starting at AAA, follow the left-right instructions. How many steps are required to reach triple Z? This does not seem hard. Like, it's a bit of parsing work to get this input, but it's fairly simple parsing. We can just do it with string splits again. As for this, yeah, this is just going to be a string and we're just going to cycle it. What does the full puzzle input look like? The full puzzle input has a longish string of directions, but not that long. Let's make this bigger. And there are not that many nodes in the graph. And they're all 3 letters long. Alright, so the plan is we write a parser to parse this. Then we just walk through this and count the number of steps. Let's see how this goes. So we're doing this in Livebook. We start by creating a new notebook. Let's call it AoC 2023 day 8. We are in day 8 today. We save this to avoid any nasty surprises later on. We are going to need Kino as a dependency because we're going to be using it to read input. And then the first section is going to be called helpers. Like with every previous day, we start by creating 2 text areas for the input. Actually, we're going to have two examples today. Text area. Example. This is example 2. And then this is going to be our full input. Let's call it full. Let's copy our examples in so that we don't have to keep referring back to the problem statement. That's one example. Here's the other example. And finally, the full input. And now, new block, part 1. Okay, so first off, we read the input. We read the example input. And so first off, we're going to split on double new line to separate the directions from the network. This should give us a list of 2 lines of 2 elements, where the first element is the directions, and then the second element is the network. We're going to match on this. Let's call these pairs and network. And then we're going to plop this into a map just so that we can pattern match on it nicer later. Yep. Now we're going to have to parse the network. So let's do that. Network is network. First, let's pipe it into string split on new lines to separate the lines. Okay, and now we have one line per node. However, we also have a trailing empty string because our inputs have a trailing new line. We could just remove the new line from the input, but we can also just handle it programmatically by passing the trim option to string split. All right. Now we need to parse each of these nodes. So first we do an enum map because we have to process each node individually. Then each node we're first going to string split on equals. In fact, we're going to string split on space equals space. Okay, and now we have the node name and the left and the right separated. And here we can actually do this. Oh, we can do this in a much more clever way, in a much more brittle but much more elixir way. So instead of doing string splits here, let's pattern match on the actual string. So we're going to match on node, then on space equals space, then actually space equals space, open parentheses, then on left, then we have comma space, then we have right, then we have close parentheses. Then we're going to return node, left and right. This isn't quite right. We need to somehow tell Elixir that this is supposed to be a 3-character binary. So what's the syntax for this? Elixir pattern matching. I've already opened this page multiple times. It's going to be called something like binary. Where's pin operator? No. Pattern matching. Where's Elixir binary pattern matching? Binary strings and charless. Perfect. So this is how you match on a binary of arbitrary length, but what we want is binary size 3. There are a couple of other modifiers that can be useful when doing pattern matches on binaries. The binary size n modifier will match on n bytes in a binary, which is exactly what we need. So we want binary size 3. And this is also binary size 3. This is also binary size 3. Now this should work. And it does. So we are now parsing the input. We are now parsing the network as the node name, then left, then right. We're probably going to be doing lookups in this thing, so let's turn it into a map where the node name is the key. So here we add one more level of tuples, and then we enum into this into a map. We convert it into a map with enum into. Now we have a map. So we have a map, and then we have left and right. Actually, going by the way the input is structured, this should also be a map, where this is where L maps to this, and right and R maps to this. So let's do that. So this is now going to be a map, and then here we're going to use the character L to map to left, and the character right to map to right. This looks a bit awkward because Elixir doesn't realize that this is a character, so it's displaying it as an integer. But it is what we want, I believe. Okay, so now we have the input parsed. Next we have to walk the dirs. Oh, and in fact, dirs, we should just split this into a char list. Char list. Right. So now we have the input parsed. Next we just have to walk we now have to follow the directions until we reach ZZZ. And we are going to put this in. How are we going to do this? There's probably some enum function that lets us do this, but it'll be much clearer if we do it with a recursive function. So let's just pipe this into part 1, follow dears, and we start in AAAA. Now we create a module, call it part 1. I have to create a module because Elixir doesn't let us define functions at the top level. Then we have follow dears, we have the node. Let's call this data. And then here, let's do follow dears AAA and data. We need to pass the data in so that we know what directions to follow. But piping it in would result in... Yeah, piping it in would have resulted in data being the first parameter, and I'd really rather it be the second parameter. Here, data. How do we do this? So I'm now thinking that we're also going... our state... Alright, let's just write more of it. So node is definitely a binary. It is the name of the node. Data is our little map that has dears and network as keys. The interesting bit here is that we also need to have an index into dears to know at which direction we are currently following. Well, all right, let's write it bit by bit. Network. All right. So we also need to somehow say which direction we're currently at. And here where I said string to char list, I'm now thinking that I actually want to say string to char list to tuple, and then list to tuple. And then here, let's just return dears. What does this return? This returns a tuple of the directions. Can we do it with a cycle? So there is such a thing as stream cycle. Creates a stream that cycles through the given enumerable infinitely. This is kind of what we want. But then I also want to take, how do I match on the first element of the stream? Is there a split? So there's clearly a take. Take lazily takes the next count elements from the enumerable and stops enumeration. Right. Is there... Well, there's probably a num.split, but the num.split is not quite what I want, is it? A num.split splits the enumerable into two enumerables, leaving count elements in the first one. Okay, let's try this out, because this is what Livebook lets us do. So we start with RL, this is our input. Next we convert it into a char list. Next we pipe this into stream cycle. And if I evaluated this, it will probably hang. No, because it's lazily evaluated. But now I pipe this into a num.take1. R. Okay, what happens if I pipe it into a num.split1? Now it hangs because it's trying to evaluate the second element. Right, so split isn't quite what I want. What happens if I do... Wait. So take one does what I expect. I can also do stream take one, right? This gives me a string. This gives me the actual stream. So if I do stream drop one, this gives me the new stream. And then if I do here enum take one, it should give me L. Okay, so it's a bit awkward, but we can do it with this combination of functions. Right, so here, instead of converting into a tuple, let's convert into a stream cycle. Does that make sense? No, we can do this better. We can do this better. Okay, so first off, let's not complicate our data parsing function any further. We start with AAA and then we pass it data.network because we need the map. And then separately, we also pass it dirs piped into enum to charlist, well, string to charlist, and then stream.cycle. So now our function takes 3 arguments. The node we're currently in, the next directions we have to follow, repeated to infinity, and then the actual network. So here, follow dirs. It takes the node, then it takes dirs, and finally it takes network. Which is the map. And does stream have an is stream? Is stream? It does not. What does a stream even look like? A stream is some sort of function. Can I do this? I cannot. Okay, so I have no idea what the stream is or how to match on it. But that's fine, this is probably good enough. Okay. So now we're going to do direction. Dir is dirs.enum take one. This is going to give us the string, right? This will give us enum.take one. Let's put this in a new section of its own, and let's branch it from helpers so that it doesn't keep evaluating the previous section. Okay, so this gives me the char list R. So here, where I said the character L, I actually wanted, oh, and I can write this like this. So here, when we create the map, we're going to do it with a char list instead of characters. Okay, so this is our current direction. Our next directions are going to be dirs stream drop one. And then, actually, first off, we do case network of node. Case network of node of dir. Do. If we end up in ZZZ, then we're done. Otherwise, we have a new node, so we're going to we have a new node, so then we just have to recurse into it. Oh, and we don't actually have to do this like this, do we? No. We can do it with top-level pattern matching. So first we compute dirs, and then we just do follow dirs of network of node of dir. And then we have dirs, and then network remains unchanged. And here, if we do follow dirs, and we end up in ZZZ, if we end up in ZZZ, then we are done. And we are done actually means we should return the length. The length, which will now be our fourth argument. And the length increases by 1 every time we recurse. And the length starts at 0. And here, because this is probably broken in some way that I don't understand, let's IO inspect the node. Right. Here, dirs. There is no such thing as dirs. There is indeed no dirs. It's data.dirs. Okay, so executing it, we get AAA, then CCC, then 2. So we start in AAA, then we go right once, which gets us into CCC, and then we go left once, and we end up in Z. Okay, this actually worked. Let's try it with example 2. This also worked. Okay, maybe it just works. Let's comment out our IO inspect and try it out with the full example. It's running for quite a while. Yeah, let's stop it. Let's uncomment our IO node and see where we're at. What's going on? This is just going to be a really long evaluation. Because there are some obvious ways of optimizing this. Like, we could find all of the cycles. We could find the cycles ahead of time and then somehow go speed run through them, skip them, when instead of going through the elements one at a time. Okay, let's stop this. How many of these is it doing per second? If so, here we are. If rem of len and 1,000, I wonder how many nodes it's processing per second. Do. Output S. We are currently at len, and we are currently at node. Oh, I forgot the equal sign here. I forgot the actual comparison. Okay, this is way too slow. It should be doing way more than 1,000 steps per second. Okay. If I had to guess where the slowdown is, it's going to be in the stream cycle craziness. But it does not pay to be clever. Okay, so here instead we're just going to do enum dot to tuple, list to tuple. So Elixir and Erlang do not actually have arrays. They do, however, have tuples, which is kind of the same thing. So here, we start at 0, yes, and then the direction is going to be lm of dirs and length, modulo something. Modulo length of dirs. Is this a thing I can write? So going back to our little experimentation ground here. Enum list to tuple. Okay, can I pipe this into length? No, length does not work. What is it called? Do we have a tuple length? Tuple size? No, we have an actual function called tuple size. Is it called tuple size or is it tuple.tuple size? Tuple size. All right. So here it's not length, it's tuple size. Right? Then theirs doesn't have to be modified in any way. And then this should just work. Now we try it back on our first example. No function clause. Right, because now we're again doing it with characters. Okay, now we try it with the second example. We did it with the second example. Now let's try it with full. Yeah, look at this. Like, it computed instantly. So it turns out creating lots and lots of streams by calling stream drop is a bad idea because they're lazily evaluated functions of some sort. So it was probably just building up a stack of a function that calls a function that calls a function and so on up to a depth of 13,000, which just doesn't work. Right, let's see if this is the right answer. That's the right answer. You're 1 gold star closer to restoring snow operations. Okay. Can we clean this up in any way? Let's just comment out our little debugging code here. And that's much nicer. We now just have the answer and no noise. Okay, let's go to part 2. Part 2. The sandstorm is upon you and you aren't any closer to escaping the wasteland. You had the camel follow the instructions, but you've barely left your starting position. It's going to take significantly more steps to escape. What if the map isn't... Oh, let's make this bigger. What if the map isn't for people? What if the map is for ghosts? Are the ghosts even bound by laws of space-time? Only one way to find out. After examining the map a bit longer, your attention is drawn to a curious fact. The number of nodes with names ending in A is equal to the number ending in Z. The number of nodes with names ending in A is equal to the number of nodes ending in Z. If you were a ghost, you'd probably just start at every node that ends with A and follow all the paths at the same time until they all simultaneously end up at that end with Z. They all simultaneously end up at nodes that end with Z. Why would they simultaneously end up at nodes that end with Z? For example, okay, and we have 2 nodes that end with A, and we have 2 nodes that end with Z. Here are 2 starting nodes, 1A and 2A, because they both end with A. As you follow each left-right instruction, use that instruction to simultaneously navigate away from both nodes you're currently on. Repeat this process until all the nodes you're currently on ends with a Z. Repeat this process until all the nodes you're currently on end with Z. If only some of the nodes you're on end with Z, they act like any other node and you continue as normal. In this example, you would proceed as follows. Okay, so our termination condition is different. We terminate not at triple Z, but at any node that ends in Z, or rather at when we reach all nodes that end with Z. Step 1. You are at 11A and 22A. You choose all of the left paths, leaving you with 11B and 22B, right? Because 11A goes into 11B and 22A go into 22B. Then we take both the right paths because the next instruction was right, and this gets us to 11Z, and then 22C. Right, and then we follow this, and then we don't stop even though we found the Z, so we just continue iterating until both of them reach 11Z and 22Z. What's the deal with XXX? XXX looks suspicious. XXX looks like it loops back on itself, so if we ever end up in XXX, we will never terminate this algorithm. So in this example, you end up entirely on nodes that end in Z after 6 steps. Simultaneously start on every node that ends with A. How many steps does it take before you're only on nodes that end with Z? Okay, I don't know what the performance characteristics of this are going to be, so we need to do a bit of experimentation. So first off, let's split this up. Let's start a new section. It's going to be called part 2. Our parsing code is the same, so let's just move it to a new module up here. Let's call it the module AoC do def read input. And as our input, we're going to take a Kino input, and then we're going to be doing this whole thing. Next, we indent this. And then here, does this compile? It does not compile because we're reading full instead of input. We want to read input. Okay, that compiled. So here we should be able to just replace data with read input of full, and the result should be unchanged. (13:207). 13:207. Yep. Okay, so we now have a way to read the input easily. So let's do read input example. Again, we need to specify the module. And it's called example 1. And now I'm curious how many nodes in the network terminate in AAA. As in, how big is our herd of nodes that are moving forward? Not values, I want keys. Okay, now I have all of the key names. Okay, and now we pipe these into enum.filter, or rather, we pipe this into enum.count. And then we have an str, and it will be just string.ends with str, and suffix is a. So only one node is in the first example, only one starting node in the first example, only one starting node in the second example, and in the full example, 6. Okay, then I think we just brute force this. Of course, the problem is that it might... Okay, so I know how we make this better, but we're going to try to brute force it first. So the problem is when we actually... So when we're going to run this, we're going to find this interesting situation where 11A gets to whatever something.z in 23 in let's say 5 steps, and then 22A gets to something z in, let's say, 7 steps. But of course, as we're evaluating this, we won't be able to stop when we do the 5 steps here, because this one will have not terminated. So we'll have to iterate on them, and then the actual iteration will stop at 5 times 7 is 35 steps. So we can either just walk this manually and do all 35 steps, or we can try to compute this and hope that I guessed correctly. Because really, it's not going to be... This is the easy case when we have 5 and 7. But we can also have a much more annoying version of this, which is 4. And... this is A. And let's say this one is going to be 8. And now we don't stop at 4 because the second one hasn't reached its end. We instead stop at 8. So it's not 4 times 8, but 8. So what we want here is the lowest common multiple. So we stop at lowest common multiple of path 1, length, path 2, length, and so on. Yes, let's just do it the right way around, because I really don't want to debug performance problems in Elixir. Okay, so let's move this a bit below so that we can look at it later. Now, back to here. We read the input. Let's also get the new example from them. Let's get this new example so that we can do debugging on it. So here, let's do example 3. We copy paste it. And now here we will be working on example 3. Yes, and we have our 2 starting points. So what I want to do here is, instead of just calling follow dears once, I want to call a follow dears once for every key that ends in an A. So first off, let's find all the keys that end in an A. I probably shouldn't have deleted the previous code. Oh well, we'll manage. Network. I don't care about dears, but I will care about data. Okay, network. So we do the thing again where we do network .map.keys. And this time we do enum.filter. And we're going to use the shorthand syntax to define a lambda. That's string.ends with first argument and then A. This is starts. And then we're just going to put starts into our data. Right, so our starts are 11A, 22A, and we still have everything else. Next up, we are going to compute for every one of the starts. We're going to call follow dears for every one of the starts so that we find the length of the path it takes until the end. So, another then, and this time we're going to need all the bits. So dears, network, starts. Now this whole thing with the then is a bit annoying to do, so let's just break it up. Yeah, this is much nicer. Alright, so now we do enum.map on starts. And here we just call part1 follow peers. We start at start instead of AAA. Then we have to do this whole thing, so let's just copy it and do it ahead of time. We'll probably move this into our parsing code later on during refactoring. Anyway, there's the network, and then 0. Okay, I screwed something up. What did I screw up? Start deers. Follow deers is trying to go all the way. Here we go. Follow deers is trying to go all the way to ZZZ. And instead, this time I wanted to go to any node that ends in Z. So let's add another argument here. Yeah, so the ending condition. The ending condition will be one is... So the ending condition for... I know. Here, this is part 2. Alright, so the ending condition is string.ends with Z. And the ending condition for part 1 is going to be equals to ZZZ. And now follow deers here, instead of doing this thing, it does node cond, can't call it cond, and when end of node. And here we also take end as an argument. Then here we just threaded the end argument through. And now part 1 should still run. Can't invoke add1 inside guards. Alright. So here, if end of node to len, else we do the old stuff. So we can't do it with the top level match, but that should be fine. And this is Elixir, so we have to use the special syntax. Calling a lambda in Elixir requires us to use dot open parentheses. And Joseph Alim has a blog post explaining why this is necessary, why this is somehow required by the parser. Alright, and now we look at part 2, and if we run this, string ends with 2 is undefined. Oh, I'm missing a question mark here. Alright, so part 2, we're now saying, let's include more data here. Let's include start and also the end. Yeah. So for part 2, we're saying that 11a needs 2 steps to get to the end, and 22a needs 3 steps to get to the end. Is this correct? So 11a gets to the end in 2 steps, and 22a gets to the end in 3 steps. But then the two of them have to get to the end in the lowest common multiple of 2 and 3. Alright, do we have an LCM function in Elixir? We do not. So we need to write our own LCM function to compute this. How do you actually compute lowest common multiple? I bet you factor it and then you take the maximum number of prime factor, the maximum count of each prime factor. But let's just quickly check. Lowest common multiple. In arithmetic, notation, applications, calculation, using the greatest common divisor. The lowest common multiple can be computed from the greatest common divisor with the function. Okay, how do we... Wait, is what I said correct? Using prime factorization. For each number and factor each number and expressed as a product of prime number factors, yes. The LCM will be the product of multiplying the highest power of each prime number together. Okay, so yeah, I described it correctly. But what's the greatest common divisor? Can this be computed more easily? Calculation using prime factorization. The greatest common divisors can be computed. Let's make this bigger. The greatest common divisors can be computed by determining the prime factorization of two numbers and comparing factors. For example, to compute this, we factor it, and then it's the minimum of each factor, which makes sense. So this is not particularly easier for us. Oh, they have a simple algorithm. Let there be a finite sequence of positive integers. The algorithm proceeds in steps as follows. On step M, it examines the sequence. Yes, is the mth iteration. The purpose of this examination is to pick the least, perhaps one of many, element of sequence xm. In other words, the least element is increased by the corresponding x, whereas the rest of the elements pass from x to x to m plus 1 unchanged. Okay, so what's this algorithm again? So on each step m, it examines and updates the sequence. The sequence starts with the list of positive numbers, where x to the m is the mth iteration of x. Yes, okay, so we take all of the numbers and then we do something with them at every step. We pick the least, perhaps one among many, element of sequence x. Okay, so the least element of this sequence is 3. Assuming xm is the selected element, the sequence xm plus 1 is defined as x to the m plus 1 is xm when k is not the least element, and if it is the least element, we add 3 to it. So we start with 3, 4, 6, then we add 3 to 3, so we get 6, 4, 6. Then we add 4 to 8, so we get 6, 8, 6. Then we're going to add 6 to 6, and we get 6, 8, 12. Then here, why are we adding 3 here? Oh, because we always add the element from the first. So the smallest one here is going to be 6. So we add 3 to itself. Then the smallest one on the next step is 8, so we're going to add 4 to it, 12. This doesn't actually look all that slow, to be all that fast, to be honest. I think I'd rather just do the prime factorization. Yeah, let's write some prime factorization. Haven't done this in a while. I wonder what the actual values are for full. Yeah, look at this. These are not large numbers. We don't even have to be clever with our prime factorization. Okay, so let's write a function called factor. The module part 2, we have to put it in a module. Then we're going to do factor of n. Yep, and then factor of n is just going to call factor of n and 2. the factor of n, and let's call this I. When I is less than s squared, is s squared here, I think? No. When I times I is less or equal to n, I'm just going to do the really boring algorithm where, yeah, we just try all of the factors. I don't think I've written one of these algorithms in over 10 years at this point. If lambda n and I is 0, then we found the factor. So we're going to return I and then const on top of factor of n divided by I and still I. And if it doesn't divide, then we're just going to return factor of n and I plus 1. And then when we're done, we just return an empty list. So here, let's recall part 2 factor of, let's say, 6. It says 2. It should say 2 and 3. Does it break if we say 2? Nope. 3? Nope. What happens if we say 12? Arithmetic error. Because presumably we're not doing whole division here. What do we have? We have rem, but surely then we also have div, right? We have div, performs integer division. Right, so here it's not n divided by I, which gives us a floating point number, it's div. Okay, 2, 2. That's better. So what's going on? Let's IO inspect this. Let's IO test this, in fact. So we start with 12, but then we try 2. And 2 divides, so we try it again with 6. 6 divides, so we try it again with 3, but 3 is not going to be less or equal to n. Okay, this is better. So what happens if we call it on a much larger number, say 125? Works. 250, this should be 2 and then 3 5s. Also works. How can we do this better? Here, instead of doing factor and 2, let's also then pipe this into unknown frequencies. Okay, so now 2 to the 50 is composed of 2 to the first power and then 5 to the third power. Okay? So now what happens if we pipe our actual numbers into this? Our actual path lengths into this? We get this. Oh, that's interesting. All of them are exactly 2 prime numbers raised to the first power. Really? I guess it must be true. Wait. Is it? So this is just, yeah, these actually do look like 2 prime numbers, the product of 2 prime numbers. I guess that must have been the easiest way to generate the test input. Okay, so now we have these, and we are going to merge these maps and pick the lowest, what we want the lowest common multiple, so we basically want a map that has all of these keys and then has the lowest the lowest value for each of them. So do we have something like map merge? We do have something like map merge. Merges two maps into one. All keys in map 2 will be added to map 1, overriding any ones in map 2. That's not good. Here. Merges two maps into one, resolving conflicts through the given function f. All keys in map 2 will be added to map 1. The given function will be invoked when there are duplicate keys. Its arguments are key, value, and value2. The value return will be the new value. Okay? So here we do map merge. No, we don't do map merge, we do list reduce. We do enum reduce. And then we have factors 1 and factors 2, and then we're going to call map merge on them. Map merge fs1, fs2, and then the function takes the key, which I don't care about, and then it takes the power from the first one, the power from the second one, and we're just going to return the minimum of power 1 and power 2. No, and this is not 2, this is power 2. Okay, and now we have to recompose this into an actual number. So we're going to do enum.reduce. We'd start with 1, then we get a number and the power, and we get a tuple of a number and the power and also our accumulator. And then we return our accumulator multiplied by our number raised to the power. And I forgot an end here. This gives us a big number. Is this how you raise a number to a power in Elixir? 2 to the third. Yes, this is how you raise a number to the power in Elixir. Okay, so this looks like a really big number. Let's see what happens if we try to submit it. That's the right answer. Okay, we kinda YOLO'd this one, but it worked. Okay, so we have the second gold star for the day, and we're done with at least the initial stab at this. Return to Advent calendar. Yep, this is now done. I'm glad we did the more complicated thing with the lowest common multiple, because iterating through this would have taken forever. Like, look at this, it's millions, billions, trillions. This would have taken probably hours to iterate through, maybe even days. Okay, I triggered the Livebook weird interaction here, so I need to reload. Okay, let's clean up our code just a little bit. And for the most part, this is fine. But we can remove some deduplication. For instance, in both our parts, we're doing this char list tuple conversion. So let's just move this into read input. Here. Right, and then here we don't need to do this whole thing anymore. And now if I run this, it errors out here. What did I screw up? Oh, it's not data.ders. Here it's just called ders. Okay, this compiles, and here the result shouldn't change. And here the result shouldn't change. It did not. Can we... is there any more code we can share? We can delete this debugging code. But no, we're already reusing the follow function from part 1 here. Where is it? Here, we're already reusing part 1 follow ders, so we don't need to share that. We don't need to deduplicate that. And then the factoring in part 2 is good enough. Like, this is pretty terrible code to factor a number, but hey, it works. We could do something clever with a sieve of Eratosthenes or like Euler's algorithm or something, but we just don't need to because the numbers are so small, it's unnecessary. This map merge here is also not the greatest code ever written, but hey, it works. Can we shorten it? Can we code golf this a bit? Let's indulge. So this is argument 2 and this is argument 3. You cannot skip arguments, all arguments must be used, so we cannot indulge. Elixir will not let us write ugly code. Can we code golf? We could probably code golf this, but no much point in doing so. Okay, then I think this is it. We've solved the problem. Where are we on the leaderboard? Or where are we? We're not on the leaderboard, but we are on the stats page. So, a lot more people solved solved yesterday since we last looked. About 30,000 more people solved yesterday, and unsurprisingly, almost everybody who solved part 1 also solved part 2. Today, the number of people that has solved the problem completely is higher than yesterday, but a lot more people seem to be struggling with part 2, which is unsurprising. This is one of those cases where you can actually write an algorithm that completes in O of heat depth of the universe. And the numbers continue to decline day by day. Okay, well, that's it for today. Thank you for watching and see you all tomorrow.